Here is a memory organization or hierarchy. You see, at the bottom you see tape is a memory device. This like a cassette, audio cassette. It was the serial data storing and retrieving method on a magnetic film. I mean plastic film on which magnetic metal is sprayed, and on that magnetization is done for 1. If not magnetized, then it is 0. Like that, information is stored. This is a serial read-write method can be done here. I mean to say, if you say like a cassette, if you want to listen this song of the last song in the track or in the cassette, then you have to rewind. Okay, then only you can do that. Similarly, this is also the case. Same thing. Serially, you can do 1 by 1, or you have to first forward or do something like that. Until it's going to that particular location, you cannot access the data from that location. Then your disk. This is your hard disk. It is a magnetic tape. This is possible. Then a hard disk is DD. Sometimes this hard disk drive indicating that, and hard disk will be there inside. In this hard disk platter, kind of hard platter will be there, or rigid platter like a plate, multiple plates, and the right head will be there. This memory tape is very slow, very slow, very slow. This is a little faster than tape. It normally in the hard disk normally 7,200 RPM. We have discussed already. Okay, the speed revolution per minute, and then main memory. Main memory is semiconductor memory, that is DRAM. Okay, DRAM, dynamic RAM, made up of one MOSFET. And first cell is made up of one MOSFET and one storage capacitance. I think we have discussed. Pratham is there?
Yes, sir.
So we have discussed or not DRAM?
Yes, sir, we have discussed.
Okay, then this is all external. See, magnetic tape, hard disk, or even DRAM are external to the processor. Processor is here in this dotted box. All the components, 3 components you can see, that is the processor, registers, and cache. This is one chip in which all these things are there. So in which, if any memory is there, and that is firstly the cache and registers. Two things there. Registers, if you talk about the registers, then, and if you take the processor example of 8085, then it is having register like accumulator, which is also called A, then temporal register, then B register, C register, D register, E register. Individually they are 8-bit register. Individually they are 8-bit register. They can be combined also. H also individually 8-bit register. L also individually 8 register. These are 16-bit register. PC and SP. Stack pointer and program counter. And you have external DRAM, this thing, okay, of 64 kilobyte in 8085 processor. Okay. Anyway, I am relating this with a particular processor, but the diagram here or memory hierarchy given here is a generic. Okay. These values may be varying from processor to processor. And the question is, processor very high speed, okay, whereas the tape is very slow. So to increase the speed, the faster hard disk was developed, but still the processor is so fast compared to hard disk that processor will send a signal for read operation or write operation from the memory, okay, or the hard disk. It has to wait for a long time, like a day for it, okay. It is so fast. So to bridge the gap between the processor and the hard disk, another memory was designed, that is DRAM. Okay, DRAM was quite faster, much faster than disk. Okay, of course, this disk term is a very generic. It may have a floppy disk. I mean, floppy disk. It may have two type of floppy disks we have discussed. Then it may have compact disk CD and DVD and hard disk. All are included in this disk term. Okay, all are slow. Of course, out of these, floppy disk, DVD, CD, and hard disk. Hard disk is the fastest. Okay, so possibly hard disk actually hard disk should be kept in separate category, like compared to other two. Here you should put floppy disk, and here you can put CD or DVD. Okay, then it will be better because hard disk is quite faster than this disk. So anyway, still main memory. Main memory was quite faster than all those memories at the bottom, but still it is much slower than the processor speed. Okay, so to bridge the gap between the processor speed and the memory speed, a very high speed memory is placed inside the processor, that is called cache. Okay, cache, and this cache may be three level of cache: level 1 cache, level 2 cache, and level 3 cache. Okay, if you see your processor, you will see this kind of configuration. Your laptop will also describe this processor. Cache memory will be specified by L2 or L1, etc. Then other than this, you have the registers, and registers, as I said, that this kind of registers will be there in the memory, in the processor itself. So this is particularly for 8085 processor of Intel. It may be a little different, name may be different, or bit size, or word size rather, per row, the byte or word or double word I have said. So that may be differing from processor to processor, maybe from Intel to AMD, etc. Anyway, my point was that the hierarchy of memory here is indicating that someone is very slower, so high speed memory has been designed. Then that is also not sufficient. So another finally cache has come inside the processor, and register also are there. Okay, so normally in our lab we do research on cache memory for your studies and project, etc. You see, you might see my applications mostly on cache memory. It is called SRAM, static random access memory. SRAM. Okay, 6 transistors is required. The industry standard was 6 transistor MOSFETs is required in this. So with this, well, we are a little out of context here, but this concept should be clear to you. Why some faster memory, why slower memory? Is capacity wise very small capacity. Remember that. Okay, this is higher capacity, higher or larger value can be a larger data can be stored. Now we'll go to the next slide to continue our discussion on memory and its decoding, plus memory cycles, read cycle and write cycle, etc. Few definitions here. Firstly, the access time. When you try to read content from the memory, the time required is called the access time. We call normally in our research terminology read access time. Access time. We denote it with TRA. TRA. Read access time. And for write operation, we use write access time, and we say TWA. Here terminology, whatever is used, you go with that. For reading, it is told read, not read, just access time. Okay, the access time of the memory read operation is the maximum time from the application of the address to the appearance of the data at the data output. Okay, on the bus. This is the definition of access time. Whereas for write operation, the write cycle time is the terminology used. It is the maximum time from the application of the address to the completion of all internal memory operations required to store the data. Okay, so these definitions would be used for your case because it is taken from your book. You go by book. Okay, read for read operation access time, it is told. For write operation, it is called write cycle time. Okay. One example is taken of a CPU which is having a frequency of 50 megahertz, and 50 megahertz will give a period of frequency is 50 megahertz. 50 into 10 to the power 6 hertz, and period will be what? Period is equal to, or time t is equal to what? T is equal to 1 of f is equal to what? 1 upon 50 into 10 to the power 6 hertz. I'm sorry, second. Okay, or if you write it in this way, it is 1 by 10 to 5. How much in this period? Period will be 5 into 10 to the power 7. I'm writing, and then I am writing 1 divided by 5 is what? 0.2 into 10 to the power minus 7. It becomes, I am multiplying with 100, so it is 10 to the power minus 9. Is it not? So 1 nanosecond. Period is 20 nanoseconds, and 1 nanosecond is 10 to the power minus 9. So is it okay? I mean, for this example CPU. Yes, Pratham. Pratham, are you hearing me?
Yes, sir.
Okay, net was giving problem. Anyway, we'll continue. So,
Hello.
so is it the calculation? I mean, telling that 50 megahertz CPU is taken, and hence its period is 20 nanoseconds. Is it understood?
Yes, sir.
Pratham? Okay. Suppose now that CPU communicates with the memory with an access time, that is read access time of 65 nanoseconds and a write cycle time of 75 nanoseconds. Right? This is assumed. Read delay is less compared to the write delay. The number of clock pulses required for a memory request is the integer value greater than the or equal to the larger of this access time and write cycle time. That means how many clock cycles will be required for this memory request will be how many clock pulses in this case? Since the period of the CPU clock is 20 nanoseconds and the larger the access time, larger the access time and the write side time is 75. So 4 period is required actually, and 80 nanosecond is at least 4 period means 80 nanoseconds, but before 5 nanoseconds the write operation will be completed. Is it not? Yes.
Yes, sir.
5 minutes before 5 nanoseconds before the write operation can be. So 4 clock cycle, at least 4 clock pulses are required to complete this memory access. Memory access means both reading and write operation. Reading takes less time in this example, 65 nanoseconds, whereas write operation takes 75 nanoseconds. So because of this 4 period is required now. Let us have a look on the timing diagram. Write operation is discussed first, and this write cycle is discussed. So in this, that the address has been placed or made valid on the address data address lines, and on the rising edge of the clock, T1 rising, you are applying. Okay, and memory enable signal, which is also nothing but chip select signal. We have discussed about this, is also raised or made high at the same time, same rising edge of T1. But write operation, for write operation, you make low read write bar. You see, read write bar. If this line goes high, then read operation will be performed. If this line goes low, then write operation will be performed. One line is good enough to. We have also discussed earlier and drawn also circuits, block diagram like this. Block diagram, in that I have shown that you have say 8 line input. Okay, input, this I say 8 line output. You have controls. In one of the diagram I have said the write read control and write control, and another is enable. This enable or CS, chip select or select line. Okay, so these are the things we have discussed. Three controls or one. It can be one only. Read oblique write bar. If you write bar if you use, then only one is good enough. Both are not required. So we have understood that. So this enable signal is lowered for write operation at the rising edge of T2. Okay. The write cycle in part one. Part one means this diagram is talking about. Shows 4 pulses T1, T2, T3, T4, because we know 75 nanoseconds is required. So with 3 we cannot do. 3 pulses is not sufficient for write operation. 4 at least is required. Okay, with a cycle time of 20 nanoseconds for a write operation, the CPU must provide the address and data, address and input data to memory. What it has to do for write operation, you'll be sending the address, it will be enabling the chip or chip select, it will be sending the control, that is write control. For that you need to make this line 0. Then you have to supply the data input for write operation, and that is given after 1 clock pulse later. Okay, so that's what it is given here at the rising edge of T2. Okay, So, and you see here that will go to next slide. You see here it is the valid data up to this point, but before that your write operation has been occurred. Okay. Then after that you are able to uh, uh, make it high once again, the read write signal. Okay. A change of the read write signal to 0 to designate the write event. This once you are making it was read write signal was high here. Okay, up to this point. Now it has been lowered at this point onwards. It is indicating that you are performing the write operation. Okay. It is happening at the rising edge of T2. Okay. To avoid the desktop data in the other memory words, it is important that this change occurs of the signal on the address lines have become fixed. Means address are up to this point, address are now settled. Okay. You know, address should be settled. Address is what? The bits. It is traveling through a bus, and every bus is going to offer some, delay, RC delay. RC time constant, you understand, I hope. So let it be settled, then you send the data. Otherwise, some wrong location will be written with the data. That's what is said here. Okay. Otherwise, one or more other words might be momentarily addressed and accidentally written over with different data. That's what is telling. The wrong data written should not happen. So you send the data once address is valid. I mean, and it is selected. I mean, what line? This address is going to send what? Select line will be ELB decoder, and that address is going to make one of the word line 0. I mean, WL1. Okay, this kind of I have shown with the decoder earlier. Yes or no?
Yes, sir.
So those one of the line will be high. Select line it is. You can say we have discussed select line. That select line is going to be connected to a particular bit cell. We have seen. So same thing will happen. Okay. So it has to go first to the memory, then data will be sent or valid data will be available there for writing operation. The read-write bar signal must stay at 0 long enough after application of the address and memory enable. Address is this one, memory enable this one. So your this read-write should be kept low for long time, so that the write operation is completed. Finally, the address and data signals must remain stable. Address as well as data signals will be stable for a long time. For a short time after the read-write goes on, I mean to say the address and data signals must remain stable for a short time after the read-write goes high. Here is talking about. Okay, I mean read-write signal write operation was going on. Now you are rising. After this time is the. After that also you have to keep this data high, and this memory. Sorry, address is also kept high. Memory enable is also kept high for a certain amount of time. Okay. So we have discussed about settle, I mean, or that whole time, then setup time, propagation delay, etc. Can you remember? Why at all we have to keep data valid for some time? Yes, you so that all these requirements of the storage elements is satisfied. Setup time, hold time, propagation delay, etc. At the completion of the fourth clock pulse, see, fourth clock pulse is ending at what? This is the starting point. So ending point of T1. This is the starting point, ending point of T2. This is the ending point of T3. This is the ending point of T4. Okay. So what is said here? The memory write operation has ended with 5 minutes to spare. I mean, we know 75 nanosecond is required. Okay. So nanosecond is required for write operation as per our assumption. But this from here to here, it is not here to here. From here to here. From here to here, it is 80 nanoseconds. You know, per clock cycle is what? Or sorry, clock period. Per clock period is what? Total
20.
20 nanosecond. It is mentioned here. So it is going to be 80. But our assumption is still that 75 nanoseconds required. So possibly here things will be completed. Okay, this is your rise time. This is your fall time. This is false width, and together from here to here it is 20 nanoseconds. So prior to that, 5 nanoseconds prior to that, end of this T4, the write operation will be completed. During that time, you see another operation may be started. That's what is told here. And the CPU can apply the address and control signals for another memory request with the next T1. Next T1 is coming here. This one is next T1. During that time, you can start another read or write operation. Now read cycle. I mean, bottoms diagram will be looking at. Okay. See here also, on the rising edge, you have applied the rising edge of T1. Is address is made valid, means the processor has sent the address to the data bus for the memory decoder. Okay, and that in case of 8085 processor, it will go through pins AD0 to AD7 lower byte. Okay, lower byte of address will go 16-bit address. Remember that lower byte, and upper byte will be A8 to A15. Okay, your PC is 16-bit. Remember program counter. So address is 16-bit address, and 16-bit address you can access 2 to the power 16 is what? Kilobyte. Kilobyte can be accessed. 2 to the power 16 means PC is going to send the address through these lines or pins of the 8085. 80 to 87 is the 8-bit, another 8-bit is here. Okay. Why I have written 80 to 87? Can you say? You have not yet studied, so you will not be knowing. This through this lower and this lines and these lines pins, address as well as data can be sent and received. Okay, address will be outed during the first clock pulse T1, and then through the same line data can be sent or received afterwards. So that's what happened in 8085. In other processor may be different. So anyway, this whereas this upper byte is sent through A8 to A15 pins of the processor, and this is only dedicated for address, not for data. But this is, I mean, for both. This is for both. It is bidirectional. Remember that data will be outed in this direction, all be received. Outed for write operation, okay, and received for read operation. Read means you are reading from memory. Okay, so it is bidirectional. Anyway, let me come back to the topic what we are discussing. See, read operation see the first clock, rising of the first clock, you are sending the address. Okay, enabling the memory. Chip select you can say, or enable signal you can say. Then read write you are making what? High. For read operation, it is to be what? High or low?
Hi.
High. It is high. It is high, or let me write 1. Okay. And see, data output is invalid. This shaded portion is invalid data. Okay, you are not able to read this data into the processor through this 80 to 87 lines. Data will be valid when after a delay the memory will be outing the content on the bus through read buffer, write buffer, read buffer, output buffer, and it will be now valid, and it can be processor will be taking this data into itself, okay, into its register actually, like accumulator, B register, C register, etc. So the CPU applies the address, sets the memory enable to 1, and sets read write to 1, to designate a read operation, all at the positive edge of T1. Everything is happening at positive edge of T1. Okay. Address also sends, enable sends, made high, read write made high. Okay. Data is going to be read from the memory. So initially data is invalid. Okay. And the question is how processor will be able to know the data is valid or not. There will be a provision. Memory is much slower. Okay, processor has to wait. It will be inserting the wait states. When you'll read a microprocessor, this terminology will be used. Memory is slower. Processor is faster. Memory for read operation, what it will do? Send the address, enable signal. It will send. Read write signal will be sending to making high and waiting for the data. Okay, because the memory is going to take certain time, and it has to wait. So it will insert the wait state. I mean to say 1 or 2 clock pulse is not sufficient. Okay, suppose at this point after T2 it is trying to access the content of the bus. What it will get? It will get the wrong data, because data is not valid. So how it will come to know that the data is valid? It is coming from the memory. There will be a signal coming into processor. Suppose you decide you have the processor, so a signal will be coming. That is ready signal, RADY. This ready signal, once is going high, then it will understand that the data available into the data bus is valid. Okay, that will be taught to you later on. Now, is it understood? Read operation.
Yes, sir.
Timing diagram only we are discussing. The similar things will be discussed later on in microprocessor. The memory places the data of the word selected by the address onto the data clients within 65 nanoseconds. It takes 65 nanoseconds here. See, it is denoted here. Written here 65 nanoseconds required. After that, only data will be valid. Okay. Then the CPU transfers the data onto the one of its internal registers during the positive transition of the next T1 pulse. The next T1 is this one. During that time, it is going to take the data inside its register. That register may be accumulator, B register, C register, or any other register, D register. Various registers I have said. Okay. Now, regarding array of SRAM, we have already discussed to full strength, extent, but still we'll have a little relook onto it. Here you see that this chip is 64 by 8 RAM. Means what is meaning by 8? What is meaning by 64K?
485, 4.3.
Some noise is coming.
That is
Put up your mic. Now, Pratham, can you say what is meaning of this 64K by 8 RAM? What is the meaning of that?
Sir, address is 16-bit and input is 8-bit.
Input is 8-bit, address 16-bit. 16-bit address is okay because written here you are telling, but otherwise what you understand by 64K by 8 RAM. 16 to the power 16 means what? 64K.
64K.
Okay, 1K is 1024.
24.
1024. So if you multiply with 64, you will get those many 64 into 1024. What is the value? Tell somebody, calculate and tell me. And then those many addresses are there, means those many rows are there. Are you getting my point? Yes or no?
Yes, sir.
Those many. What is the value?
65,536.
65. Then
536.
536. Those many rows are there, and every row is having how many bits?
16.
Where you got it from?
Eight.
It is 8-bit. Everyone, see, it is, if I divide it, it will be 8-bit. 1, 2, 3, 4, 5, 6, 7, 8. 8-bit. 8-bit information will be stored in one address location, and we have 65536 addresses. Those many rows are there. Okay, and this, as you can see, that input data is there. 8-bit address is PC will be sending this address in case of 8085. This input data will be coming from AD. As I said, that AD0 to AD7. To that 8 pin, it will be coming. Data will be coming in this direction. Okay. Or if it is read-write memory RAM, then it may be going out also from here. Okay, to this RAM inside the processor. These are the pins of 8085. And PC, program counter, is a register, internal register of a processor. To that, those registers and address are sent out. Okay, it is coming to the decoder of this RAM. Remember that. It is coming to where? Decoder or not? Yes. You will have decoder here. Input will be 16-bit. Okay, and you will have how many lines, you say, of the decoder? I was telling WL0, etc.
88027.
WL, let me write. First one is WL0. I was writing WL1, WL3, and 2, etc. So last one will be what?
WL7.
No, you have the 16.
WL15.
Hmm.
WL15.
How?
Sir, 16 bit of address is there.
Aman, Bushra.
Sir, WL3, 2 to the power 460.
So you have the input to the decoder. So two input lines are there in the decoder. How many will be here? How many will be here?
4.
Sir, 4.
4. If you have total 16, then
2 to the power 16.
what is that?
65536.
Then why you are mistaking? You have started with 6553 till what? 5 or
Five.
6.
536.
Understood? Those many rows are there. Now it is clear.
Yes,
You
sir.
have to address, point to that those many. Those lines are becoming high to, and it is going as a memory select or chip select, memory select line or enable line. Okay? That you have seen. I have shared in the bit cell. Bit cell. There is a select line. Okay. There is an input. There is an output. And there is a read a write bar. Can you remember that? At the beginning, I said with the bit of information. These are the information. This is the output. All three are input. Are you remembering?
Yes,
So
sir.
the select line, as the select line input, the 8-bit data input is coming. Okay, that is 8-bit in this case. Okay, and address. After decoding 16-bit is here, and one line is coming here high, and it is going to select. Okay. Similarly, if you have eight flip flops, okay, because 8 bits can be stored in a row, so 8 bit cell will be there, and all bit cell will be selected in this way. Are you getting? Yes or no? Suppose this is a WL0, so you have 8 cells, bit cells, isn't it? The select line will be coming here and it will be enabling. Yes or no?
Yes, sir.
Yes, sir.
8 will be there, they will be selected. Then you are sending the read write control signal. That will also go everywhere, isn't it? It will be going everywhere. We have seen a lot of things in this regard. You must be able to remember all those things. Output, one is coming out from here. Similarly, will be coming out from here and here. The 8-bit will be coming out, isn't it? Yes or no?
Yes, sir.
So this is the things about this. Let us go to the next slide. I hope something you have understood. Something or completely. 64K by 8 RAM. If I say, are you understanding this?
Yes, sir.
Okay. The same thing only. Some chip select. We are talking about the chip select. It is kind of enable. Okay. Enable signal anywhere, many places you have done, and that is chip select input. Select the particular RAM. Complete chip to be selected. You may be using more than one chip. I will see the example later on. And the read write is bar here. Read write bar should be given here. Okay. Input specifies the read or write operation. We know that. If it goes high, then read. If it goes low, then what? Right? Yes or no? Just now in the timing diagram, you have seen that. If this line is high, then which operation is going to be performed?
Read.
Read. If it is 0, then write. Okay.
Right.
Okay. So 8 bits are there, so 8-bit output line is there. Now let us read the last bullet. When chip select equals to 0, the chip is not selected because it is having no bubble. If it is a bubble, having a bubble, suppose, then it would be considered that it is a active low. It is now active high. So once it is 0, it will not be selected, and all its data outputs are in the high band state. With CS equals to 1, the data output lines carry the 8 bits of the selected word. Means to say, if this is 0, and you have, say, inside only, you have a buffer, that tri-stated buffer. Have I discussed anything about the tri-stated buffer? And symbol for that is what? Okay. Yes, kind of this. Tri-state buffer, did I say? We have discussed many things in the first or
No, sir.
not discussed. Tri-stated. Okay. So we have discussed, but you are not remembering tri-stated things. When you are discussing about the TTL, etc. During that time, we have discussed. But the symbol also, I have shown. If you want, I can show that, but you are not remembering. Tri-stated. So with the MOSFET itself, I'll be able to tell you what is this things. I have shown you. It's not new. Tri-stated. Let me tell it here only. I don't know whether you'll be able to understand here or not. Say it's not a place to do. Tri-stated buffer, I'll be talking about what how to get a space. Not getting a space. Okay, I'll make it. I'll take a blank space here. Just wait. I am going to talk about the tri-stated buffer with MOSFET, right? Okay. Suppose what is this MOSFET? And what is this MOSFET? Tell.
So top one is PMOS, bottom one is
NMOS. Okay. Okay. I connected in this way parallelly. Okay. And then now I'll be taking this space too. When CS goes high, it is this is CS equals to 1. This is 0 or not?
Yes.
Yes.
0.
So P MOSFET is on because its gate is 0. Yes or no?
Yes, sir. NMOS is also on.
Also on. So on this switch, it is a kind of switch. It's called transmission gate. The switch is on. Okay. Switch is on. So the in value of in whatever is say 1, that will be going through this switch and out also will be 1, isn't it? Do we agree or not? Switch is closed means it is conducting, and MOSFET is also conducting. The MOSFET is also conducting. Both are conducting, so in will be whatever, that will be the out. If in is 0, out is also 0, right? But suppose CS is 0. Let me take another color. Suppose you are taking CS equals to 0, then what? What is the CS bar? That is 1.
Yes.
This is 0. So what about the conductivity of this 2 MOSFETs?
So they will not conduct.
They will not conduct. So in will not get path. Whatever is in doesn't matter. In will not get path to out. So what is the status of output node? It is not connected to anywhere. I mean, it is in high state, right? So that's what is written. The 0 CS is making high beta state. CS1 data output lines carry the 8 bits of selected. I mean, if you have 8 lines here, you will have that kind of 8 this kind of switches, tri-stated switch or TG based, or you can say multiplexer kind of things. Okay? So 8 will be required here. This kind of symbol is maybe this kind of buffer symbol. This is going to make this. If it is 1, then in is equal to out. Okay, whatever in is, that is out. Understood? Yes.
Yes, sir.
Here you have some smaller RAM chips having 64K by 8. 64K by 8 understood? K by 4 RAM is understood, no? Now you are using that and you are going to make 256K by 8 RAM. Okay, so 4 is required here. 4, and they have been connected in this way. So decoder has been used. So every 64K by 8 RAM is requiring 8 bit of information for input data or output data. If it is RAM, you can read and write. So input output both is going to go through this. Possibly our output is having the same outline, but input is coming through 8002, 87. Of course, it may go back to a processor through that same line. Anyway, the 16 address lines is coming here. Okay, everywhere. I mean to say every here 16 line is there. Okay, but the 16 line you can address only to the power 16 means what is that? You have calculated
65,536.
65,500. What is that? 63. 36. So this many can be accessed. So you are going to access more, 4 times more. No, 4 chips are there. So 4 times means to the what? 2 more address lines are there. So that is here given to the decoder, and decoder is going to give 4 output. And when these 2 are 0 0, this one is going to be high. If select or not, this is high. Yes.
Yes, sir.
When it is 0 1, this one will be high. Okay, and when both are 1, this will be high. So at a time only one chip is selected, and from there one row is read, and that also depends on which row is read. That depends on these bit patterns of the 16-bit address. If this all the 16 bits of the address is say 0 0 0, all 16 bits are 0, then the zeroth row will be giving the output through these two this output buffer, or say bus. It will be going into the bus. What is bus and all we'll be discussing a little bit. This is nothing but parallel lines, okay, through which signals are transmitted or received. Okay, so similarly, when this 0 1 is given, then data will be going through read from the second chip, from the second chip means from the top, from this. Okay, when this address line is 1 0 address lines, these 2 address lines for decoder, then it will be read from here, and if it is 1 1, then it will be read from here. Now which row is being read, that depends on the bit pattern of this or address of the 16 bit. Is it understood?
Yes, sir.
Of course, we have discussed a lot. Here, what you are finding? Your number of row is not sufficient, and because you have a 64K row, or this many rows, 65536 rows there. That is not sufficient for you. This memory, those many bytes are not sufficient for you. You need more, 4 times more, 2 times more. So 2 chip, 3 times more, 3 chip, 4 times more, 4 chip you are connecting. Is it not expanding of memory and decoding? Yes.
sir.
I think we'll end up here. Now, if your byte having 8 bits and your 64K by 8 RAM is having only 8 bit in a row, that is not sufficient for you. So you need 16 possibly. Okay, then you can connect in this way, and we have discussed earlier also, isn't it? Yes, Pratham?
Yes, sir.
We have discussed many things about the expansion, so that is also over. We don't want to speak anymore. These diagrams are taken from your book. Earlier I have taken from different book. Otherwise, basic thing is same. All will be CS is going to here and here also, and parallelly connected. So both the chips will be parallelly selected, and hence you will be getting 8 bit means 16-bit outputs here when the memory is read. Or when you are writing, 8-bit here going to this chip, and another 8-bit going to in this chip for write operation. Of course, along with that, you have to address it properly. And read write control has to be given. It is given to everywhere the same thing. Okay? If you are writing, same W bar will be there, write bar will be there. And if you are reading, then read write will be one. So it is very simple. Now we will be starting something new called programmable logic design, programmable logic arrays, and programmable array logic. This will be, I think, last topic of this. Then we'll go to the fifth module. Something left over in the first module, that will be visual Verilog fundamentals that we'll be discussing later on after fifth module is complete. So PLD, programmable logic device, is a generic name given to a group of integrated circuits, certain kind of circuits that can be configured to perform desired logic functions. It has fuse links to be configured. ROMs, PROMs, EPROMs are programmable but are not normally classified as PLDs. During programming, fuses are blown that must be disconnected so as to obtain a particular configuration. The gates in a PLD are divided into AND or array or flame that are connected together to provide an or SOP implementation. The initial state of PLD has all the fuses intact. I mean to say, it is a class of, chips, integrated circuits, and normally ROM, PROM, EPROM are not classified into this. And it is having AND flame or flame that we'll be seeing very soon. And there are various symbology we have to understand. In this diagram, the diagram A is showing a cross on the junction. It is indicating that the linked or fuse link is there. Okay, it is not fused, it is still intact. Okay, and B is telling that the fuse which was placed during the fabrication is no more there. It has been fused, means there is no connection between A and B, line A and B. Is it understood? And the C one is telling that there is a permanent connection here between the line A and line B. Yes, these terminologies or you can say symbologies are to be remembered. Intact fuse, intact fuse is intact, means it's there. Here no fuse link, or fuse link is blown. and it is a permanent condition. Now there are this will be, I mean, this kind of symbology will be used later on very soon. So you remember that. Types of PLDs. There are 4 types here, and they are PROM, programmable ROM, PAL, programmable array logic, PLA, programmable logic array, and GAL, G, generic array logic. Okay, we'll try to discuss one by one, starting with say PROM. PROM types. There are 4 types are there in PROM itself. There are 4 types. First type is fabricated by the vendor, means the chip maker, foundries, or maybe vendor may be ordering and making the chip and selling out in the market. So semiconductor company makes it on the basis of the submitted truth table by the customer. Okay, it is costly due to special fee for custom masking, if not mass produced. Means if a vendor is giving its truth table and making some chips, so definitely the foundry, whatever, generally they are making some chips. It will not be like that. They are processing steps, or chip making steps may be different. Whereas you are giving a new things, new truth table. According to that, they have to make. So fee may be a little more. And if it is not fabricated in a batch, mass produced, if you don't do, it's not mass produced, then it may be costly. For small quantity, it is more economical to use a second type of ROM called the programmable read-only memory, or PROM. Customer in the lab can blow the fuses. Initially, when fabrication is done, fuses will be intact, but later on, it can be done in the lab by the customer who is purchasing by application of some high voltage pulses using PROM programmer to the device through a special pin. Okay. A blown fuse defines a binary 0 state, and an intact fuse gives a binary 1 state. Can you remember, Pratham, we have discussed about the diode ROM?
No, sir. I can't remember diode ROM.
Diode ROM, Rishi, I mean, Harsh Tripathi. Bushra is absent today.
Yes, sir.
Diode ROM, can you remember?
Yes, sir.
In that, presence of diode was indicating what?
Sorry, now I remember, sir. 1, sir.
1. Absence of diode was 0. Okay.
0.
Similar kind of things is done. Diode is doing what? It is conducting and connecting that horizontal line with the vertical line, isn't it? Remember that?
Yes, sir.
Diode
Yes, sir.
connecting the horizontal line with the vertical lines. Okay. Here, instead of diode, you are using fuse. Okay. Its name is changed. Okay. So a blown fuse defines as 0 or binary 1. Sorry, is binary 0 or low. And if there is a fuse, then it is indicating a binary 1 state. The same way, we have already discussed that thing, and that discussion is good enough to understand all those things. The third type of PROM is the erasable PROM, or EPROM, which can be restructured to the initial state even though it has been programmed previously. And for that, you need the UV light. We have also discussed all those things. The fourth one is the electrically erasable, or flow talks we have discussed, isn't it? It is getting repeated. So I'll just leave this topic quickly and go to another topic. So at these things, we have discussed about 4 type of PLDs. from PAL, PLA, and GAL. Now, what kind of, as I said, that and or plane will be there, array or plane, okay, in this PLD. So, which one is having what? Which one is the programmable? Is it and plane is programmable or plane is programmable? That we are going to see now. Programmable means there will fuse. You can blow the fuse and disconnect the connection. Okay, that's the way you are going to program. Disconnect the connection with the vertical line and the horizontal line means you are in absence of diode, indicating 0. Here in from, what is there? Fixed and array and programmable or. Remember from in which or array is or plane is programmable, whereas and array is fixed. You cannot program it. In PAL, programmable array logic, or is fixed. That's reverse case. Or is fixed and plane is programmable. It is reverse case. Okay. It is reverse case or not? It was earlier not programmable. It is now fixed like that. So here in this case, both are programmable in PLA and as well as or planes are programmable. Internal structure is given here. PLA with 3 inputs, 4 product terms, and 2 outputs are given here. Okay. Should I continue discussion or time is over? What is that?
Sir, time is over.
Okay, then we'll stop today. I'll continue in the next class. Today you have the quiz. Are you remembering? Yes. Pratham.